Welcome to the Data Science Seminar. It's a great pleasure to introduce Professor Melanie Weber. She's an assistant professor at Applied Math and Computer Science at Harvard University. She got her PhD in Princeton at the Math Department in 2021. Her PhD advisor was Professor Charlie Pfefferman. Then she went for a one-year postdoc at Oxford. She was a Cook Fellow, and then she joined Harvard. She has general interest in different geometric methods, analytic methods in machine learning, and she is a recipient of the IMA Leslie Fox Prize in Numerical Analysis of this year, and also a Simons Berkeley Research Fellow and a Princeton CV Star Fellow. She's going to talk about exploiting geometric structure in matrix value optimization.
Thanks a lot for the introduction and for the invitation to speak here. And it's my first time in Minnesota. Great to visit here. So my talk will be on exploiting geometric structure and matrix value optimization, and all the work that I'm showing is joint work with Suvrit Sra, who's a professor at MIT. Let me start with just one slide, sort of very broad overview on the field of Riemannian optimization on the task of optimizing functions on manifolds. So the general problem that we're looking at in this field is to compute efficiently a solution to the following problem. So our objective function is defined on a Riemannian manifold, and then we want to find the minimum of that function, potentially subject to constraints, but not always. Problems of that form, so this is a pretty general problem class, and that might arise in many different settings. Here are three examples that are sort of adjacent or related to machine learning, which is sort of the broader area that I'm working in. So the first one is sampling. So recently there's been a lot of interest in studying sampling algorithms through a Riemannian lens. So in particular, we can view a lot of sampling algorithms, such as the Langevin algorithm, for instance, as optimization in Wasserstein space, which is one way of parameterizing the space of probability densities. And then it has been found that results from the convergence analysis of Riemannian optimization algorithms can be used to derive convergence results for sampling algorithms. A second area where we encounter Riemannian optimization problems is generally in geometric machine learning. So here we train machine learning models on geometric domains. And then the optimization of the training loss involves a Riemannian optimization problem. And then lastly, and that's the area from which we will see numerical examples and applications in this talk, is matrix valued optimization. So here we are interested in machine learning algorithms or subroutines in classical machine learning algorithms that involve matrix valued functions. And here we can often view these problems as an optimization problem on a matrix manifold, and that will lead to some algorithmic benefits that we will see in the talk. So in particular, two kind of tasks or types of problems we want to look into. So first, in order to perform optimization on Riemannian manifolds, we have to extend classical Euclidean algorithms to the Riemannian setting. So we, of course, can't just use the standard algorithms that are designed with data lying in a Euclidean space in mind, but we have to generalize them to Riemannian manifolds. We might also sometimes use tools from Riemannian optimization to analyze classical algorithms because there's some geometric structure in the problem that is better analyzed with Riemannian tools. And we will see examples of both of these directions in the talk. So to zoom into this third area of applications of matrix valued functions that arise in machine learning, you see here on the slide just a small selection of such problems. Many of those classical algorithms or subroutines I'm sure you have encountered in your work, such as barycenter problems. So if you want to average collections of matrices, or things like k-means clusterings or minimum bisection, those are all problems or algorithms that can be phrased as Riemannian optimization methods. Here I've written what types of manifolds, for instance, we can parameterize these problems on. you see here a lot showing up PD, so that means the problem involves positive definite matrices, and we can raise this problem on the manifold of positive definite matrices. And in fact, all the numerical examples that we will see in this talk are of this form, where our function is defined on positive definite matrices. So classically, one might approach a problem of that form with Euclidean optimization methods. Right, if we're having a function that's defined on matrices, matrices can be seen as vector spaces, so we can use classical Euclidean optimization tools. And in that case, the constraint that characterizes the class of matrices that we're working with enters as a constraint. So if we're optimizing over orthogonal matrices, then we have an orthogonality constraint. Or if we're optimizing over positive definite matrices, then we have a positive definiteness constraint. You probably know that in general, it's easier to do unconstrained optimization as opposed to constrained optimization. So in this context, it's a good idea to rewrite the problem on a suitable manifold that implicitly encodes the class constraints of the matrices that we're working with, right? So instead of doing constrained optimization with an orthogonality constraint, we could work on the Stiefel manifold. Or instead of imposing a positive definite constraint, we could phrase our problem on a manifold of positive definite matrices that implicitly encodes the positive definiteness constraint, and we don't need to worry about constraint optimization setting. Now, another algorithmic benefit that arises in this reparameterization, and that will underlie most of the things that we see in this talk, is geodesic convexity. So we will see that there are functions which, with respect to the Euclidean metric, are non-convex. But if we phrase them in this Riemannian setting, then they are convex with respect to the Riemannian metric, and we'll define that properly in just a few slides. And then we know that in general, it's always easier to solve a convex problem as opposed to a non-convex problem. So if we can reparameterize a problem in a way such that it's geodesically convex, that helps us when we want to solve the optimization problem. The two types of Riemannian algorithms that we will see in this talk are as follows. So in the first part of the talk, we will actually talk about algorithms for constrained Riemannian optimization. So here, in addition to the class constraint that tells us what class of matrices we are optimizing over, we have additional constraints that arise from the problem structure. This could be like a bound on the norm of the matrix or the determinant, or inequality or equality constraints. And we see that actually, as you see on the boxes on the slide, that in a lot of applications, especially in the machine learning context, where we would like to apply such methods, we have these additional constraints. So just working with a classic extension of an unconstrained optimization algorithm is often not enough in these settings, and we need algorithms that can actually handle constraints. Now, you may ask, haven't we done this reparameterization to get rid of the constraints and be able to work in an unconstrained setting? Why would we choose to work in a Riemannian space if we have to handle constraints anyways? The reason here is really this geodesic convexity. So if we have better convexity properties in the manifold setting, then it is much easier to solve a convex constraint problem as opposed to a non-convex constraint problem. So in that setting, the reparameterization really can give us algorithmic benefits. In the second part of the talk, we will look into problems that have another special structure, namely where our objective function can be written as a difference of convex functions. And here again, there are some benefits that we can get from geodesic convexity if we have that structure in a problem that we like to solve. And it turns out that especially in the matrix valued optimization context, there are a lot of classical examples of difference of convex functions that are geodesically convex, and where we can exploit that structure for algorithmic benefits. And that will be the second part of the talk. So before we actually move on to part one, I just want to, on one slide, briefly define geodesic convexity, which we have already mentioned a couple of times. So this inequality that is written here on the slide will look very familiar to you if you've seen, as I'm assuming, Euclidean convexity. If we're in the Riemannian setting, right, so our objective function is defined on a Riemannian manifold, then a geodesic is the shortest path between 2 points on the manifold along the manifold. And now if we want to check convexity, we have to check convexity along the geodesic, and that's exactly what's written here. And if we were to specialize to the Euclidean case, then that geodesic would just become the straight line, and then this condition would just turn into the classical convexity condition. In the optimization context, geodesic convexity has the same nice properties as classical convexity, so it guarantees that there's a unique optimum to our minimization problem, meaning that if our algorithm finds a local optimum, we can be sure that that's the global optimum. Or in other words, we can get global optimality certificates from essentially any initialization. And that's a very powerful property in optimization that we want to make use of. So let me now move on to constrained optimization. So that problem is a slight specialization of what we've seen on the initial slide. So we have the usual objective function that defined on a manifold that we're trying to minimize. And now we put the additional assumption that our minimum has to lie in a certain convex region of the manifold, which we call script X. We have to assume that that subset is convex. That's very important for the class of algorithms that we will be defining, also that it is compact. We also have to assume in this setting that our function is smooth. And it may be convex or geodesically convex or non-convex, but the interesting cases are certainly where it is geodesically convex. And then just to remind you, there are several sample problems that fall into that class of problems. So if we want to design a constrained optimization algorithm, I should perhaps say that a lot of work in the Riemannian optimization community has focused on the unconstrained setting. So precisely for the reasons that I mentioned earlier, to reparameterize Euclidean constraint problem as a Riemannian unconstrained problem. So there hasn't been too much work before that on algorithms that can handle constraints in the Riemannian setting. In order to maybe find a starting point for extending, for designing constrained optimization algorithms for Riemannian settings, we can, as is often done in Riemannian optimization, have a look at what's been done in the Euclidean setting. And in the Euclidean setting for constrained optimization, there are essentially two classes of algorithms that you typically see: projected gradient methods and projection-free methods. Projected gradient methods are essentially a straight extension of gradient descent to the constraint setting. So the idea is simple. You can see it here in the little schematic figure. So if we're at an iterate xk, an iteration k, then we evaluate the gradient to find descent direction, and then we perform a classical gradient descent step. Now, of course, that gradient descent step doesn't take any constraints into account. So what might happen is that we step outside of the feasible region where our constraints are valid. So this is shown here, but we're outside of the feasible region, which is shown in blue. And then in order to get a valid next iterate, we have to make sure that we stay in the feasible region. So we project back onto it. And then depending on the geometry of this set shown here in blue, the feasible region, that projection may sometimes be very easy to compute or very expensive to compute. And it turns out if we're in the Riemannian setting, so if our domain also has a geometric structure, that those projections are often not very cheap to compute. In that case, it might be worth looking into the second class of algorithms, namely Frank-Wolfe algorithms. Frank-Wolfe algorithms also evaluate the gradient to find descent direction, but instead of performing an update step right away, they call a subroutine, which is called the linear oracle, that you see here. And what that subroutine does is that it looks in the descent direction to find a point that just fulfills the constraints. So in our case here, that's the point zk that lies on the boundary of the feasible region. And then we don't want to get too close to the boundary of the feasible region. So we, in the Euclidean setting, linearly interpolate between the 2 points and then step with a certain step size along that line. And that since we have assumed that the feasible region is convex, will always give us a point in the feasible region, and we don't have to worry about stepping outside and projecting back. So in other words, if it's easier to solve the subroutine, the linear oracle, than it is to compute a projection, it's always better to use a Frank-Wolfe method. So for the projected gradient methods, if we're now moving to the Riemannian setting, gradient descent was one of the first algorithms that's been extended to the Riemannian setting. So that would be a very natural extension. But again, it turns out that this projection is usually difficult to compute in the Riemannian setting. So what we set out to do was to see whether we can extend the Frank-Wolfe algorithm to the Riemannian setting. So in order to do this, we essentially have to look at the two key ingredients in the algorithm. So one of them is, of course, the linear oracle, that subroutine that finds sort of the endpoint of for constructing our update. And then the second one is the update itself. This linear oracle is in the Euclidean setting constructed as like a linearization. In the Riemannian setting, we have to like search along a geodesic in the descent direction. So here we have to replace the Euclidean gradient with the Riemannian gradient, and then also parameterize the subproblem along a geodesic that's written here with the exponential map. And then our update step itself is not a linear interpolation, but also again a geodesic interpolation. So here again, we see the exponential map, which roughly parameterizes how geodesics look like in that space. That also shows up here in the update step. And then if we analyze that algorithm in terms of an iteration complexity, so if we analyze how many iterations do we need to get epsilon close to a solution, then we find that that algorithm has a sublinear convergence rate, and that's the same as in the Euclidean setting. So in other words, if we take that algorithm and specialize it back to the Euclidean setting, we get the classical Frank-Wolfe algorithm. So that is in a sense, a meaningful extension of the Euclidean Frank-Wolfe algorithm. Now, if we're thinking about, so that tells us something about how many iterations we need to find a sufficiently accurate solution. But another key complexity measure of the algorithm that we have to keep in mind is to think about how expensive is it to compute one iteration. And that here depends mainly on two things: on computing the Riemannian gradient. That's in general a little bit more expensive computationally than computing the Euclidean gradient. And then also we have to think about how to efficiently solve the subroutine, the linear oracle, which is really the key computational bottleneck in the algorithm. For the linear oracle, so in the one nice thing about the Euclidean Frank-Wolfe is that that subroutine is a convex subroutine, so it's fairly easy to solve. In the Riemannian setting, it's non-convex, so we have to think a little bit more careful about how to solve it efficiently, but we will shortly see that there are approaches for doing that. Let me just comment before we go to that on the gradient oracle, so the cost of computing the Riemannian gradient. So as I said, in general, it's more computationally expensive to compute the Riemannian gradient versus the Euclidean gradient. But there are sort of some standard tricks that we can do for problems with a special structure to reduce the cost of this gradient oracle. So in particular, in the machine learning context, we often find problems that have a finite sum structure. So for instance, if you think back to the first slide, one of the examples that we had was to optimize the training loss of a geometric machine learning model, right? A training loss might have a finite sum structure, like we see down here, where maybe that's a square loss, and then M is the number of data points in your problem. So problems like with a finite sum structure arise very often in applications. And then we might also be in a setting where we have to optimize a black box function, so where we don't know the underlying objective function, but we can only query points from an oracle. So those are two classical types of problem structures that arise, but specifically in the machine learning context. So if we're working on geometric domains, we have to be able to handle problems of this structure. And then I just want to mention very briefly that we can extend this Riemannian Frank-Wolfe algorithm that we have introduced also to these settings. So if we're in the Riemannian setting, we don't have access to the true Riemannian gradient. We can only estimate that. For instance, with like a classical technique from stochastic optimization called the Robbins-Monroe approximation, which can be extended to the Riemannian setting. And then as long as we can control the approximation error of the gradient estimator, we can show that that algorithm still converges, albeit at a slightly slower rate. And then importantly, in the finite sum setting, we can also extend the algorithm to that setting. Here we use a variance-reduced gradient estimator. So basically here the idea is that we, imagine that M is a very large number, right? We have a sum with many, many terms. And then we don't want to compute the gradient of that function in each iteration because we essentially have to compute M gradients. So we just sample a subset of those M terms and then average over those. And then only every couple of iterations we compute the full gradient and use that as sort of a reference point. And one can show that that allows us to get a sufficiently good approximation of the Riemannian gradient to still make the algorithm converge at a reasonable rate. In particular, so I said we have a slightly slower rate, so we're converging still at a sublinear rate, but at on the order of, we will be on the order 1 over square root of k close to the optimum, as opposed to 1 over k after k iterations in the setting where we have access to the exact Riemannian gradient. And then, of course, in the finite sum setting, in each iteration, we greatly reduce the cost of computing the gradient because we only compute gradients of a subset of the terms. So overall, that results in a much faster algorithm, which we will see in the numerical examples. But back to the crucial subroutine and the Frank-Wolfe algorithm. So it's written again here. Again, in the Euclidean setting, that's a convex problem, so usually fairly easy to solve. That has greatly contributed to the popularity of the Frank-Wolfe algorithm for Euclidean constraint optimization. Now in the Riemannian setting, it's not quite as easy. We have a non-convex problem. So two possible approaches that we can consider is to either solve this numerically, the subroutine. If we solve it numerically, we will likely not get an exact solution, but only an approximate solution. So there we have to carefully keep track of the approximation error that we introduce in each iteration of the overall algorithm. Or we could try to find analytic solutions for that subroutine, which of course would be much preferable to having only an approximate solution. So if we solve the subroutine approximately, so in that case, we would just call something like an off-the-shelf numerical solver to solve the subroutine. That gives us an approximate solution. And then as long as that approximate solution is not too far off, we can show that we retain a good convergence rate. Of course, now here we have some dependency on the approximation error of that subroutine, but as long as that delta is sufficiently small, this still converges at a sublinear rate. And we also see numerically that if we test that with an off-the-shelf solver, we usually still see good convergence. So in general, that's a working solution for applying this algorithm to a wide range of problems. But of course, the more interesting settings are where we can actually solve the subroutine in closed form. And one such setting where we can, in fact, do this is the following. So here we work on the manifold of positive definite matrices, and our constraint set are interval constraints. So interval constraints on positive definite matrices mean, with respect to the Löwner order, that if you haven't seen the Löwner order, that basically means that L is in Löwner order smaller or equal to X, if X minus L has non-negative eigenvalues. So that introduces a partial order relation on the positive definite matrices, which we can use to define interval constraints. And then a lot of the problems that we've seen earlier on the slide, the barycenter problem, also the Brascamp-Lieb constants, it turns out are exactly of this form. So if we have a closed form solution for this problem class, then we can apply the Frank-Wolfe algorithm to all these problems. And it turns out that, in fact, we can find such a solution. I'm not going to go into the details of how you prove this, but this is how the solution looks like. It looks kind of involved, but it's much faster to compute than if we would call a numerical solver for computing the subroutine, and it certainly gives us an exact solution instead of just an approximate solution. So in practice, using that is much preferable. And then here are some numerical examples where we implemented the algorithm here for the Gaussian mean problem. So that's one instance of the barycenter problem. So we have a collection of positive definite matrices. The interval constraints here come from the matrix means inequality. So the Gaussian mean on positive definite matrices corresponds to the geometric mean. And similar to how we have for real numbers, the inequality that the geometric mean is lower bounded by the harmonic mean and upper bounded by the arithmetic mean, that same holds for matrix means. And the harmonic matrix mean and the arithmetic matrix mean can be computed in closed form. So those boundaries of the interval we get you can compute very efficiently. Unfortunately, the geometric mean cannot be computed in closed form because multiplication is not commutative. So we have to use optimization to compute a solution. So this is here we have the Riemannian distance on the manifold of positive definite matrices. So this is how this problem looks like. If you remember from earlier, that's one of the instances that is geodesically convex. And interestingly, it's Euclidean non-convex. So here we really get algorithmic benefits from working in the Riemannian setting. And then we also see here that the Frank-Wolfe algorithm is very competitive. So it's shown here in blue. The other methods here are, or at least when this paper was written, they were comparable state-of-the-art Riemannian optimization methods. And then the dotted lines here that you see are Frank-Wolfe algorithm, but with a gradient estimator. So you notice here that the objective function has a finite sum structure. So if we approximate the Riemannian gradient here by averaging only over a subset of the terms, then the gradient oracle is much cheaper, and we see a noticeable benefit in the numerics. Okay, that concludes part one. Maybe I should stop for a minute if somebody has questions. Yeah.
What's the empirical rate of convergence that you noticed? It's not in log scale, right? It's regular scale, so it's hard to compute.
Yeah, so this is what you would expect from a sublinear iteration complexity. Yeah, and the others, I should have said that the other methods are also all first order methods. So to keep it fair, we're comparing against first order methods.
So it's about the rate that you prove?
So the benefit here really comes from solving the linear oracle in closed form, as opposed to having to compute projections, for instance. Yeah. So the great numerical speedup we really see in settings where we can solve that subroutine in closed form. If you would have to solve it with a numerical solver, the saving is not as much. It really depends on the cost of every iteration, and that largely depends on the gradient oracle and how efficiently we can solve the linear oracle. Right. So this blue line, the speedup we get from being able to solve that subroutine fast, and then the additional speedup comes from the savings that we get from the gradient estimation.
Thanks.
Okay. Maybe I'll move on. So in the second part, we're staying with optimization on manifolds, but the problems that we're now considering have an objective function that can be written as a difference of convex functions. So here, importantly, the component functions f and h are Euclidean convex. And then, of course, the difference of two convex functions is not necessarily convex, right? So in interesting instances of this problem, the objective function is Euclidean non-convex. But it turns out, particularly in the matrix valued setting, there's a significantly large subset of that class where the objective is not Euclidean convex, but geodesically convex, meaning that we can exploit the geodesic convexity. We will see that for at least for the theoretical analysis. And among the simple problems that we saw earlier, there are a couple of them that fall into that setting, and we will see mentioned here and there also other examples. Difference of convex optimization is in generally has a very rich literature, both from the Euclidean and also more recently from the Riemannian perspective. So in the Euclidean setting, this is a classical setting for non-convex optimization. And in particular, one of the classical algorithms for solving difference of convex optimization in the Euclidean setting is CCCP, which is also the class of algorithms that we will consider in this talk. And then from the Riemannian perspective, there's been work, of course, on geodesic convexity, but also on difference of convex functions from Riemannian perspective. But then also looking at algorithms that need Riemannian tools for its construction. So for instance, that work that require the computation of the Riemannian gradient as opposed to the Euclidean gradient. What the perspective that we're taking here is that we're looking at a purely Euclidean algorithm. So we stay with the popular CCCP approach, but we will bring in the Riemannian perspective to understand the properties of the algorithm and the convergence behavior of the algorithm. So in a sense, we're taking a sort of mixed Euclidean Riemannian perspective. We analyze a Euclidean algorithm that sort of from a computational perspective is usually cheaper than a Euclidean algorithm if they're overall comparable, since the computation of like the Riemannian gradient and the exponential map and so forth and introduces some computational overhead. But then for the analysis, we exploit the geometric structure in the So just to introduce or remind you of the CCCP algorithm. So CCCP stands for convex concave procedure. The algorithm is very easy to derive. So I can do that here on one slide. So we first noticed that the component function h is by construction geodesically convex. Right? So we have this inequality which we get directly from the Euclidean convexity by just rearranging terms. And then we can insert that into the objective function to get an upper bound, as you see here on the right-hand side. That upper bound is convex, as opposed to the objective function, which is in general Euclidean non-convex. And then the idea of the CCCP procedure is to, instead of directly optimizing the objective function, we just optimize this convex upper bound. And then one can show that the sequence of iterates that we get from that convergence to the optimum, at least asymptotically. Since we're here in the non-convex optimization setting, we can typically not certify global optimality. We can only certify that we're converging asymptotically to a local optimum. And then it's also difficult to analyze, to give non-asymptotic convergence guarantees. So meaning to say precisely how close we are to the optimum after a certain number of iterations. And then, as I already said earlier, right, nothing in this construction of the algorithm uses Riemannian tools. We don't need to compute any Riemannian gradients or exponential map. It's a purely Euclidean algorithm. Where the Riemannian geometry now comes in is really in the analysis of this algorithm. So as we said, we're looking at a subclass of difference of convex functions where our objective function is geodesically convex. And that geodesic convexity gives us sort of an extra tool that we can use in the convergence analysis. And then under some additional mild assumptions that are usually fulfilled in practice, we can actually use that additional tool that the convexity gives us to certify first global optimality, right? We're in a geodesically convex setting, so there's a global optimum, and then we can also give non-asymptotic rates of convergence. So we can say precisely how close to the global optimum we expect to be after k iterations to certain constants that depend on the geometry of our manifold and the regularity conditions on the gradient. So in practice, if we now try to apply this to, or like think about what the consequences of that are for CCCP algorithms. So first, it's worth noting, as I said, the structure of difference of convex functions appears in many settings. So there's a large body of work on difference of convex optimization, many involving matrices. And then due to this very simple algorithm, those types of simple algorithms have been derived for many settings, usually not even with the CCCP algorithm in mind, but sort of as a general technique. People have arrived at simple algorithms for these problems that we can interpret as instances of the CCCP oracle. And then very often, while it was noted that those algorithms are very simple, right? So the only thing that we have to do is to minimize this right-hand side. More on that in a second. So it becomes essentially like a fixed point iteration depending on the complexity of that subproblem. So a very simple algorithm, and due to that, those algorithms are very popular. But oftentimes in the literature, you find only asymptotic convergence guarantees, if at all, and only for very few instances of that algorithm, you have non-asymptotic convergence guarantees. So now in the implementation of that algorithm, the crucial component is really to implement this subproblem on the right-hand side. So minimizing the CCCP oracle. And there are a number of algorithms actually for which that subproblem can be solved in closed form. So including the ones that are listed here. And in those cases, we have a very simple fixed point iteration. We'll see some examples shortly. And it's just you can implement it in a few lines. So it's a very popular method. There might be instances where the CCCP oracle can actually not be solved in closed form. In that case, similar to what we discussed for the Frank-Wolfe algorithms, we could use a numerical solver to find a solution to the CCCP oracle. That, of course, then will only be an approximate solution, not an exact solution. But as long as we're sufficiently close to the true solution, we can show that that doesn't cause too much issues, and our algorithm still converges at a sublinear rate with some constants that depend on the accuracy of the approximate solution to the subproblem. So again, the perhaps interesting cases of this in this context are the types of problems where we can actually solve the CCCP oracle in closed form. One instance of that, for instance, is if we want to compute very efficiently the square roots of positive definite matrices. We can write this problem with respect to the S divergence that you see here on the slide. And then a simple fixed point iteration for that problem was derived like many years before our work, actually by my co-author Suvrit Sra. In his paper, he only gives asymptotic convergence guarantees for that, so there was no non-asymptotic global convergence analysis known for this problem. But we see that the algorithm, the simple fixed point iteration, is very simple and very efficient. So here we compare this to a number of first order methods. The CCCP method is shown in red. So you see here that for all parameter instances, that's the fastest method. And it's on the same order as first order methods. So that also aligns with our theory from which we would expect that we have a sublinear iteration complexity. The second example that I want to give on which I want to spend the rest of the talk is the computation of Brascamp-Lieb constants. Brascamp-Lieb constants arise in the context of Brascamp-Lieb inequalities. I'm sure most of you have used Brascamp-Lieb instances of Brascamp-Lieb inequalities at some point in their work. So here are a couple of examples listed. So each of those are different instances of the Brascamp-Lieb inequality, depending on specific data. We'll define that on the next slide. But from the computational perspective, makes the problem of computing the Brascamp-Lieb constant corresponding to a datum so interesting, is that it's a special instance of the operator scaling problem. And the operator scaling problem itself encompasses a broad class of computationally very interesting problems. Other instances are maximum likelihood estimation, for instance, robust subspace recovery, Tyler's M-estimator, and so forth. And if one could find good algorithms for solving the operator scaling problem, then that would give good algorithms for a wide range of other algorithms. And there's a lot of interest in understanding the complexity of the operator scaling problem. So by looking at a special case here and approaching it from the perspective of difference of convex functions, perhaps we eventually get some insight into the operator scaling problem. So just to recall what Brascamp-Lieb constants or Brascamp-Lieb inequalities are. So in the most general form, we can write the Brascamp-Lieb, or in this context, in the most general setting, we can write the Brascamp-Lieb inequality like this. So this inequality is characterized by a set of linear transformations, and then some associated with that non-negative real vector that gives the exponents. And we evaluate non-negative functions. So the characterization of those components is called the Brascamp-Lieb datum. And then what we are interested in computing is this constant C. And whenever that constant is finite, we say that the Brascamp-Lieb datum is feasible, so it gives us a non-trivial inequality. And then moreover, we would like to find the actual value of that constant, which then has various implications for the study of these inequalities. So we want to compute an epsilon accurate approximation to this constant. And that's what I mean with the problem of computing Brascamp-Lieb constants. So this problem has received a lot of interest in the theoretical computer science literature. So Brascamp-Lieb inequalities themselves were introduced in the 70s by Brascamp and Lieb. And already in their original paper, they showed that the optimum is attained over positive definite matrices, meaning that if we solve that as an optimization problem, we can restrict ourselves to the manifold of positive definite matrices. And then the first efficient algorithm, which is still sort of the classical approach for solving this problem, is Suvrit's algorithm. He derived it in the general setting of operator scaling, but then that, of course, can be specialized to Brascamp-Lieb constants. In his paper, he also showed that his algorithm has asymptotic convergence, but was not able to show non-asymptotic convergence guarantees. Those were shown 10, 15 years later by Victorson, Alviera, Garg, and Alan Su in a couple of papers. And they used Riemannian lens on the problem. So a key ingredient in their proof of non-asymptotic convergence of Suvrit's algorithm was geodesic convexity. So what they derived here, so they derived polynomial time guarantees, but it's actually conjectured, and we will see that shortly in the numerical experiments, that the algorithm actually converges at a linear rate. So that would mean getting this down to order of log 1 over epsilon instead of having the polynomial factor here. And showing that is still an open problem in the general case. In some special cases, there has been made progress, but in general, that's still an open problem. And we also didn't solve this, but we came at the problem from a different perspective, exploiting the geometric structure in the problem to perhaps, for the special case of Brascamp-Lieb constants, shed some new insights or give a new geometric perspective on the problem. So in particular, the formulation of the problem that we analyzed, that's a slightly different one than from which Suvrit's algorithm is derived, is the following. So that's defined on the manifold of positive definite matrices. Again, we know that the optimum has to be attained there, so it's fine to just restrict to positive definite matrices. Notice that that objective function is a difference of convex problem. So using the usual CCCP construction that we saw earlier, we get a simple iterative map, which is distinct from Gaussian's algorithm and purely derived from the CCCP procedure. If we implement this, what we see, so here again, CCCP is shown in red. And then the other algorithms are first order methods. And we see here that we're really faster than first order methods. So we would really expect that the convergence that we should be able to show should be much faster than sublinear convergence guarantees. Our CCCP framework would guarantee for the fixed point iteration that I just showed you. So notably here, so this right-hand side, of course, comes from a closed form solution for the CCCP Argo. Yeah, which in this case we show can be solved in closed form. So implementing that, we get an algorithm that seems to be very fast. So the sublinear convergence guarantees that we get from the CCCP analysis are really like an upper bound here that is not sharp. And we were wondering whether we can make this more precise. And it turns out, in order to give a more an analysis of the problem which aligns more with the numerical results, we actually have to go sort of beyond Riemannian geometry and put a different metric on the positive definite matrices. Right, so far we've talked about analyzing problems on positive definite matrices through a Euclidean lens. Then we put a Riemannian metric on it, but there are other metrics that we could put that we could endow the positive definite matrices with. And here we go with the Thomson part metric, which is defined here on the slide. What's important to notice that does not give us a Riemannian geometry, but a Finslerian geometry. So we're in a different geometric setting. And then we want to analyze the convergence properties of that fixed point map that we get from the CCCP approach with respect to the Thomson metric. It turns out that this Thomson metric gives us a really desirable property that we are not able to show in the Riemannian setting, namely that map strictly contracts. That alone guarantees asymptotic convergence. But of course, we ideally would like to have a non-asymptotic convergence guarantee. I should also say this is subject to a suitable initialization. I'll come back to that. So assuming we have a suitable initialization, then with respect to the Thomson metric, we can show strict contractivity. So suitable initialization. So we know from a seminal paper on Brascamp-Lieb constants by Bennett et al. That the optimum lies in has interval constraints, if you like, or introduces interval constraints in our optimization problem, because there's some upper and lower bounds with respect to the Löwen order that one can derive. The proof of this statement is not constructive, so it's in practice very difficult to find a little delta and a capital delta. So that's why this suitable initialization is sort of tricky. We know that a suitable initialization exists, but it might be hard to compute in practice. But assuming we initialize in that set, then we have just from this contractivity property asymptotic convergence, and we can again with some additional ingredients can show a non-asymptotic guarantee, and actually at a linear rate, so O log 1 over epsilon rate. The additional ingredients that come in here is a regularization. So that regularization allows us to quantify the rate of contraction. And then using that rate of contraction, we are able to show the linear rate. Now, of course, that doesn't solve the Brascamp-Lieb problem entirely, because it's only up to a suitable initialization. And we, at least at the moment, cannot show how to efficiently compute a suitable initialization, because that getting that little delta and capital delta is not constructive. But if we had an efficient solution to finding a good initialization, then that would guarantee for our CCCP-style approach a linear rate of convergence. Okay, and that brings me to the end of my talk. So throughout the talk, we've seen various examples of exploiting geometric structure in matrix-valued optimization problems. In the first part of the talk, we talked about constrained optimization algorithms. References are the 2 papers listed here. And then in the second part of the talk, we talked about Riemannian perspective on difference of convex optimization and the CCCP-style analysis in the first paper, and then the second paper focuses on Brascamp-Lieb constants, so that derives the CCCP approach for Brascamp-Lieb constants and also the convergence analysis. And in the future, I hope that there are many more problems and applications in machine learning that we can apply these methods to. I think there's a lot of opportunity in general to apply geometric methods or insights from differential geometry in machine learning. Thank you.
Questions? People think of questions. So you mentioned the Taylor estimator, and most practitioners are very happy with the fixed point iteration, linear. So you have better methods, like the CCCP will work better in just the fixed point iteration? Or
also as an instance of the operator scaling problem?
Right, because what do you do when you work on a Taylor estimator?
So I'm not sure if I would imagine that the standard method for that is probably not Gobitz's algorithm. There might be, so for specific instances of those, there might be separate specialized algorithms that are used to solve them. Or so for instance, for metrics scaling, for instance, Synchron's algorithm, that would be a special case of Gobitz's algorithm. For Taylor's M-estimator, I'm not sure if that's a special case of Gobitz's algorithm. But yeah, what is mostly interesting here is the connection to all these different problems. So for specific instances of operator scaling, there might be specialized methods that are better than Gobitz's algorithm. But for the method that you have in mind, you can show linear convergence.
Yeah.
Okay. Yeah, but that might not generalize, or I'm pretty sure it would not generalize to the operator scaling problem.
Sure.
Yeah.
Do you mind going to the next slide? I'm going to click down a little bit. I'm just trying to understand so you're given I guess I'm trying to understand, you're given the F's and then you try to find the A's which minimize the constant, or yes?
Yes.
Okay, cool.
Yes. So so going from, it's a good question. So going from this formulation to the objective function that we then had down here, that requires a few steps that I skipped here. There's some variable, in principle, it's just simple variable changes. But yeah, it's probably just from the slides not completely obvious how to get from one to the other. Yeah.
So one of the fun things about this talk is the sort of hidden convexity that's present, because as an optimizer, that's fun to find convexity where you don't expect it. Do you have any intuition about this problem class, the set of functions where in Euclidean it fails to be convex, and then if I move it to the appropriate manifold, I can get the sort of geodesic convexity? Do you have any like generalized ideas about that, or are we just by seeing it in like specific problem cases?
Yeah, that's a great question. Yeah, so far it's mostly like people have been interested in particular problems and have found out that if I put the right Riemannian metric on it, I get a geodesically convex problem. To my knowledge, there's no like broad systematic theory behind how to recognize geodesic convexity or in what context it arises. But that's certainly an important question to study. Yeah, people are certainly looking in this area into studying geodesic convexity more systematically, or trying to get sort of more general convergence theory of algorithms or specific classes of algorithms that exploit that structure. But yeah, that's a good point.
How about like non-smooth problems for you?
In the Riemannian setting,
Yeah.
there's a little bit of work on that, but that's generally tricky in the Riemannian setting. Yeah, but there are a few works on that. Again, looking at like very specific problems, like if somebody's interested in a very specific application that happens to be non-smooth, and then people try to find a specific approach for that problem. But yeah, if you study like what we do here, sort of classes of algorithms, you typically work in the setting where your objective function is smooth.
So like in CCCP, if the H is not smooth, so you can't do this linear approximation so easily. Can you just pick something from the
No, so
or do you have
no,
to
we
be-
need, yeah, no, we need, so we have, if F, actually, if F is not smooth, you can handle it, but H has to be smooth, yeah, otherwise it doesn't work.
I'll ask another question. So we know in the Euclidean setting that under very mild assumptions, there always exists a decomposition of the difference of convex functions. Do you know of any papers or do you have any thoughts about there being a possible class of functions on a manifold where you could show there's difference of geodesically convex functions?
So if you, so that would be a slightly different function class, right? So
Yes.
So here we're really assuming and exploiting that F and H are Euclidean convex. If you would relax that to F and H only having to be geodesically convex, that's a different problem. There's one paper that I'm aware of, which I'm happy to send to you, that looks into that setting. But yeah, there's not much work on that, and yeah, certainly our theoretical results wouldn't translate to that setting, at least not immediately. One might be able to make it work, but it's not immediate. Oh yeah, and then so this that you mentioned, yeah, you can always write it as a difference of convex functions. That's true, but there's also in order for this to be sort of a nice algorithm, this decomposition also has to like be tractable, right, and nice. So I think there's certainly a trade-off there when you want to exploit that structure versus not from a computational perspective.
So there are instances of convex problem in Euclidean space which are kind of very slow to solve, and then you can make some non-convex formulations which are faster to solve, like a Brascamp-Lieb, for example. So do you know of some cases like this with a geodesic convexity?
No, not off the top of my head, but those might exist. I'm in my research very focused on geodesic convexity, so I might not know that.
Thank you very much.
Thank you.